Welcome. PyCon 2020 is being done a little differently this year. We're doing it online, and I haven't really done that before, but I think it's going to be fun, so let's get started. My presentation is Yin Yang Ranch, a distributed computer vision system using Python, OpenCV, and ZMQ. What we're going to cover today is a little bit about me, my farm, and my distributed computer vision pipeline, a good bit about the overall project design. I'm going to talk about the nodes portion of the design where Raspberry Pis gather and select images. Talk about ZMQ and Imagezmq, which transfer the images to hub computers, where we'll talk about how they receive and process images and event messages. And then we'll talk about how we can take questions even for this online kind of format. So I'm building a small permaculture farm in Suburbia. Permaculture is a collection of lots of practices, but it's basically trying to be much more sustainable in how we build farms and how we grow things. I'd like to read a quote for you. Remember how self-reliant a natural landscape is. An ecosystem provides for itself. No one brings in truckloads of fertilizer to a forest. No one carries its waste to the dump. The forest takes care of all that internally, producing fertility and recycling litter and debris. In other words, the forest inputs and outputs are balanced, leaving little waste, and the work is powered by sunlight. This is the model we strive to emulate. That's a quote by Toby Hemingway in his book, Gaia's Garden. So what I've been doing since I retired a few years back is I've been trying to convert my 2-acre suburban lot into a small permaculture farm. We're calling it Yin Yang Ranch. It's an evolving science project, and it's a demonstration garden. I do tours, I do some instruction here, and I'm also growing a plant polyculture. We grow lots of different things, figs, pears, pomegranates, well, and tomatoes and cucumbers, but also a lot of native plants like coast live oaks and sycamores. I'm also growing a bumper crop of Raspberry Pis. That helps me use computer vision to help manage the farm. A bit about me. Well, I went to college, starting to study EE, and I got drafted. So I learned about electronics and fixing electronics in the Army. When I got out, I went to grad school on the GI Bill. I did some dissertation research that ended up being computer science and then became a software company, where I actually wrote statistical language compilers at a time when PCs were actually a new thing. I spent about 20 years after that doing statistics and big science, big data science at big biotech. And I've also been involved since I retired with making software, building out the farm, and trying to build computer vision pipelines. I'm going to teach you a little bit more about that today. So how computer vision helps manage my small permaculture farm? Well, obviously it reads the water meter and helps me with water use. It can count bees, butterflies, and pollinators. It tracks coyotes, rabbits, raccoons, and all kinds of critters behind my barn and elsewhere. And it can monitor things that are more mundane, like does the garage open or closed, or is the driveway being blocked by a van that's delivering something. I also track sunlight hours and light intensity so I can understand photosynthesis strength and availability. And I monitor many non-camera sensors. I look at temperature, humidity, motion sensors, and solar panel output. So here's a drawing that I think helps illustrate what I mean by a computer vision pipeline. Raspberry Pis are used as nodes. They have PiCameras that take pictures, often 16 frames a second, 24 hours a day. There's 1 or 2 cameras per Raspberry Pi. And there's 8 to 12 Raspberry Pis feeding a common Imagehub. Each of them is gathering frames at 16 frames a second, but because of the logic on the Raspberry Pi, they don't send a lot of frames per day or per hour. Instead, they send only frames that are important, and we use detectors, software I'll talk about in a moment, to determine what's important enough to send. For the frames to get from the Raspberry Pi to the Imagehub requires ZMQ messaging. There's a lot of messaging services that could be used. We've chosen ZMQ, and I've even written a package, Imagezmq, to make that easy. And then once I have images in the hub, they get stored, they get filed, and I have another program in the pipeline called a librarian, and that librarian gathers as needed, things from the hub, images, event messages, processes those and answers queries. For instance, I can text the librarian and ask if the water's running. So what do I mean by a distributed computer vision pipeline? Well, computer vision is a whole bunch of techniques that capture images, resize them, perhaps transform them, and they're techniques that detect objects in images, like, is that a car or a pedestrian? Can I read the road sign? A computer vision pipeline is a sequence of computer vision programs, different ones doing different things. Initialize a camera in one program, take a picture, resize the picture, and then perhaps in another program, receive the image, and then use convolutional neural networks to recognize, say, a coyote. A distributed computer vision pipeline, is a pipeline that runs on multiple distributed computers across a network. That's what I'm doing here. I have Raspberry Pis communicating across a network to Imagehub computers in a different building, and those in turn communicate with librarian computers, some of which are in the internet. The tools I'm using for my computer vision work in Python is Python 3+. Well, we're all doing that now, right? And then Raspbian Linux for 20+ Raspberry Pis. I use both Linux and Mac OS hubs. And then I'm using NumPy, which for those of us that have been computing a long time, that's my best friend ever since Fortran at working with arrays. I use OpenCV, which is a collection of 2,500 tools for computer vision. It's the backbone of most things we do with Python and computer vision. I'm using ZMQ and its bindings PyZMQ to actually transfer images from computer to computer. I'm using the PiCamera, which I think is an astonishing device, not only for the hardware, but the software. The PiCamera module has taught me a lot about how digital camera sensors actually work. I'm also using a bunch of convenience libraries and functions. One I'll mention here is imutils. You'll see it in some of my routines. And then I'm using an array of electronics. I'm using Raspberry Pis as my main out there in the Internet of Things computers. And I'm using MOSFETs and sensors and temperature sensors, all kinds of electronics, which I tie together, mostly using the Raspberry Pi's GPIO boards. So image computing, the toolset, OpenCV. This is a big one. If you haven't used OpenCV yet, you should. There's plenty of tutorials out there. The Python bindings are great. It's one line, import CV2. It's a bit tough to install it on some things like Raspberry Pi computers, but there's tutorials out there for that as well. It runs really well on Raspberry Pi computers, actually. And the OpenCV images, you'll see them passed around in some code in a bit. The OpenCV images are easily sent as network messages because they're basically NumPy arrays. So let's talk about my pipeline a little bit. Things start at a Raspberry Pi. I call that an Imagenode. They're passed over a network using a tool called ImageZMQ, and they arrive at the Imagehub. I'm not going to talk further than the Imagehub today because this is only a 30-minute talk, and, well, that's going to be plenty. So let's talk about the pseudocode for what happens on an Imagenode. It's a forever event loop. You grab a camera image, you put the image in a queue, you use some sort of detector software to analyze the queue, decide if something happened, and then if something happened, per the detector, you send the event message, you send an image or 2 or 3, and then you wait for the hub to respond, and you process the hub response and loop forever. The Imagehub is doing something simpler. It's just listening for Raspberry Pis to send it messages. It receives the messages, stores the message, stores the image, and then sends an acknowledgement. OK, I gotcha. The Imagehub can receive from multiple Raspberry Pis at a time. I've gone as high as 15. I find that if I go much higher than 8, things start to slow down. But this is a many-in system where many Raspberry Pis send messages and event images into the Imagehub. So let's talk a little bit about how that works in Python. The upper half of the screen is the node code that runs on the Raspberry Pi. The lower half of the screen is the hub code, which in this case happened to be running on a Mac. So you import socket, time, typical Python standard library functions. I'm using imutils to import a video streaming function, and then I import ImageZMQ, which is the software that makes ImageZMQ makes ZMQ able to pass images. So I instantiate a sender in Imagezmq, giving it an address that I'm aiming at. I set up the Raspberry Pi's name just using a socket function so that now I have some text to distinguish this Raspberry Pi from another one. Then I set up a PiCamera by instantiating off a video stream and starting it. And then I just loop. Grab an image, send it, grab an image, send it, forever. On the hub side, I import CV2, which is OpenCV. I import Imagezmq because, well, that's how we're going to receive the images. And then I instantiate from Imagezmq an Imagehub. The same forever loop kind of happens again. We grab the name and the image from the Imagehub. We then use CV2 to show the image on the screen and wait a few milliseconds and then send back the acknowledgement. Now the top half of the screen shows the program that's running continuously on 8 Raspberry Pis for this particular example. And the program at the bottom is running on a Mac, which is receiving from those 8. And then it's going to display what it's showing on the screen. And there we go. So 8 Raspberry Pis are each running the program you saw at the top half of the screen. And this is the screenshot from my Mac, getting streams from all of those. I was able to get, with 8 Raspberry Pis sending, I think these were 320 by 240, sending images continuously. I was able to get about 10 to 12 frames a second. If you load it up higher than 8 Raspberry Pis, it might go lower than that. But we'll talk about it in a while. There are a lot of ways to speed this up. So let's use another distributed computer vision pipeline example. This is one I've used to teach a lot of folks how to get started in this field. It's reading my water meter. So what does the Raspberry Pi do? Well, it turns on the lights to light the meter. The meter's in the ground in a meter case. It continuously grabs frames, 16 frames a second, just watching the meter. It does ROI cropping, converts the frames to grayscale. It does thresholding so it can distinguish where the needle is. Then it detects if either the needle or the smaller needle leak spinner is in motion. And if it is in motion, it sends an event message, water flowing, and sends 4 or 5 frames. What the Mac does, acting as a hub, it receives and acknowledges those images. It adds the event messages to an events log. It stores and indexes the images. And then a separate program, the librarian, extracts digits to read the meter and keeps history of events and responds to queries about status. So here's what it all looks like. On the left is a daylight picture of what the water meter looks like. This is what they look like in most parts of the world. In the middle, this is a full frame capture from the Raspberry Pi camera. It's lit with 24 low-power LEDs. That way, by spreading out the LEDs, there's less glare on the glass screen of the meter. Once the Raspberry Pi has read the image, it processes some. It actually crops out the part of the field that isn't needed, and it picks an ROI, the little square box in the second image from the right. And if there's motion in that region of interest, it actually triggers the flowing state and sends a few images. And once the flowing state has been sent and it sent a few images, it doesn't keep sending while the meter is spinning. There's really no benefit in that. It's going to wait then until the meter stops spinning and take a reading at that time. The advantage of that is we're sending relatively few images to get the job done. And then on the Mac, the far image on the right, the Mac actually grabs out the digits, masks them out, and then it uses image classification to pick out the digits and actually read the value. So let me go back to the distributed computer vision pipeline and review a little bit about the things we've seen so far. There's an Imagehub, usually running on a laptop, a Mac or Linux, and it receives through Imagezmq images and event messages for 8 to 12 Raspberry Pis. It depends on the fact that most of those won't be transmitting at the same time, because it would be possible to overload both the hub and the network if all of them were continuously transmitting. But that's not the kind of distributed computer vision pipeline I'm building. I'm building one where events happen randomly around the farm, And on average, the network never gets overloaded. In fact, it never has been. And then the librarian and the communication hubs, those use the data that's been gathered by the Imagehub to answer questions and queries, either via a web dashboard, a texting system, or an email agent. So specialization is important, and you want the right computer doing the right job. Well, Raspberry Pis are great at some things. They're very cheap, they're reliable, they're fanless, which is important, and they're dust tolerant. They're really small, the Pi Zero is even smaller. They're very low power. They restart really quickly after power failures, and the Pi camera is great. It has adjustable settings. You can set the Pi camera in many, many different ways, and that allows for a lot of experimentation, frankly. But do not confuse that little SD card in the Raspberry Pi with a disk. It's not. It's not reliable for writing large binary image files over and over, and it writes really slowly. I can write faster to the network than I can write to the card. And you know, the Raspberry Pi has fairly limited memory, fairly limited processing capacity. It has a slower USB bus, slower Ethernet. The USB cameras don't work really well on a Raspberry Pi. The PiCams work best. But for the things it does them very well. It's really good at being out by the barn, running a camera, and being sure to capture the images and send them off on the network quickly. Well, Macs are great, or Linux laptops are great for other things, right? They're great at Wi-Fi and Ethernet fast. Solid-state disk drives really pack a lot of information in. Great computing power. They can do things like recognize the digits that are flipping in the meter much more effectively than a Raspberry Pi can. But guess what? One Mac uses as much power as 8 or 10 or 12 Raspberry Pis, and they're expensive. You're not going to put one out behind the barn to watch the coyotes. By putting some of the jobs on the Raspberry Pi and putting other jobs on the Mac, we're actually building a distributed computer vision pipeline where each computer in the pipeline does a thing for which it is best suited. Let's go over the water meter one more time, this time showing a little bit about, well, what it looks like. On the left, you can see the cover for a typical water meter container in the ground. And you can see the Raspberry Pi actually lives in a mason jar that's upside down. A slot's been cut in the top of the mason jar. The LED lights are visible next to the overturned water meter top. And when it's all assembled, it looks like the water meter cover with a mason jar upside down. You'll notice there's a 12-volt plug. I use 12 volts around a lot of my property because 12 volts travels better than 5. And then that simple car adapter, same thing you'd plug into your car's cigarette lighter to get 5 volts for your phone. That's what I use to power the Raspberry Pi. Then the images from the Raspberry Pi are passed along a Wi-Fi network. In this case, there's a Wi-Fi on the Pi through Imagezmq to the Linux laptop Imagehub that's receiving the images and text messages. That's inside the house. It's probably two Wi-Fi hubs away. And I can query the librarian program running on that and ask it, well, what about the water? And I'll get a text back saying the water is flowing. The last time off was at 9:21 a.m. Or the water's off. The last time it was flowing was at 2 p.m. So that's a complete end-to-end distributed computer vision pipeline for my water meter. So let's look at the node code in a little bit more detail. Here's an Imagenode code snippet. And this is actually the main program of the Imagenode code that runs on all the Raspberry Pis. I grab some settings. I instantiate an Imagenode, which has a lot of methods and a lot of variables in it. And then I do a forever event loop, just like the one we talked about before. I grab sensor data, which includes camera images and perhaps temperature sensor data. Then I process the sensor data by detecting motion, perhaps looking for light, perhaps grabbing a temperature reading, and I stick all that stuff in a queue, the message queue. And then, if there's something in the message queue, I send it off using Imagezmq. You'll notice some code there with a try except block to wait for a hub response. If for some reason the hub doesn't respond immediately, and it usually responds in milliseconds, but if the hub doesn't respond immediately, I actually try to fix the comm link and then restart the process. That's the actual code out of my Imagenode repository on GitHub. The thing with this approach is you need to set all those computer vision settings, and there's a lot of them. I have to set view name, I have to set detectors, I have to set lights, I have to turn on sensors. I use YAML files for that. I find them to be very helpful. They basically become a Python dictionary once you read them in. So you can see one of the YAML files on the right. It's really an effective way to put a lot of settings into an instantiation of an image node. For each image that's captured, Imagenode does a lot of processing. It applies transformations that might change the size of the image, grayscale it, threshold it, and then it applies detectors. In the case of the water meter, it's detecting motion. For each detector that's specified in the YAML file, you can specify more than one. It sends images that meet that detector criteria, and it sends event messages whenever the detector state changes. The water meter example is the most easy one to understand. The two most important jobs for Imagenode are to use detector methods to decide which images matter and send only the images that matter. For instance, when the water meter starts or stops, I need a few frames of what the meter looked like at the time it started or stopped. So I'm going to say a few more words about ZMQ. ZMQ is a wonderful transport mechanism. It does not need a broker or a server. It's completely peer-to-peer. And it is a great concurrency manager for multiple Raspberry Pis using the request-reply pattern. And as a communications protocol, it's very flexible, but your messaging protocol has to be well designed. It took me a while to work all that out. I did look at alternatives to ZeroMQ, RabbitMQ, ROS, AMQP, MQTT, a number of them. ZeroMQ really worked best for me. Although those others are well-maintained libraries with a lot of users, they may work best for you. I have taken ImageZMQ, my Pythonized version of ZMQ, and I've built a set of Python classes that allow you to move images from one computer to another. I'm using the request-reply pattern, but you can use other patterns. And it can send images, it can send images compressed to JPEGs, but the advantage of it is the images don't have to be encoded. The actual NumPy array that it makes up an OpenCV image is sent without encoding it, unless you choose to code it to JPEGs. So I developed it for my Yin Yang project. It's been tested by myself and others for 3 years. Production release 1.01 is out there, and it's currently pip installable. So install it, give it a try. If I look at the computer vision pipeline example I gave earlier, here's the places that show the ImageZMQ API. We import it, we instantiate a sender using an address for where you want it sent to. Then on the hub computer, we import it, we instantiate a hub. Generally that hub uses the localhost as its address, you don't need one. And then once having received an image, you send a reply. It's really that simple. So what does the Imagehub code look like when it's all built out? Well, this is the actual main program from the Imagehub GitHub software I put up. First, you grab the settings. Then you instantiate a hub. Then you've got that same forever event loop again. This time, it's a little simpler. We're going to wait for a hub response, input and give a hub response. If we haven't heard from any Raspberry Pi in a while, it probably means something's wrong with the network. So once we've set that patience parameter, if we exceed it before we get an image, we'll handle a timeout, which usually sends me a text and says something's broken, and then we send a reply. That loop receives images from and responds to all the Raspberry Pis on the network. So what does it do? It receives and stores images. It immediately sends an OK, stores the image, stores the message, and well, that's it. That's all that has to do. The fact that the Imagehub software doesn't do much is the key to its success. It handles images, it sends me a message if it's broken, and it runs. I've had Imagehubs running on the property now for over 2 years and 1 or 2 restarts per year. For each tuple that the Imagehub receives, it saves the image and the event message. And then the image it receives can either be an OpenCV image, which tends to be large, or it can be a JPEG encoded from that image, which is a lot smaller. And you can actually see a couple of images and the text from the log file of an Imagehub on the right. So let's take a look at one more example. This is my barn. I call it my Coyote Cam. Glass blocks infrared, so I can't use a mason jar out here. So I actually built a little cedar shake roof over the Raspberry Pi camera you can see on the right. And here's what happened. Here's an example of a fully distributed computer vision pipeline. The Imagenode is running on the Raspberry Pi on the back of the barn. The Imagehub is a Linux laptop in the house. And then the object detection is done actually on a Mac. And my detection in this case was, let's see, the coyote on the left was detected with a confidence of 63%, the one on the right, a confidence of 47%, and then the bobcat much less at 14%. It's kind of fuzzy. The images were taken with an Imagenode Raspberry Pi that was using a Pi Noir infrared camera and a 12-volt, 8-watt infrared floodlight. That Raspberry Pi captures 1 million images a day. But on the 3 days shown here, it only sent about 300 to 500 frames a day. That's an example of a distributed pipeline doing what it needs to do. It's sending only the images that matter and not cluttering up the network with images that don't. So some of the detection is done on the Raspberry Pi, and further detection is done on the Linux and Mac computers. And finally, I need to communicate with end users. So I've got a little texting routine, and it sends messages like the water is off. The last time it was flowing was at 7:15 a.m. There was an animal detected behind the barn at 3:15. Coyote, maybe, 47% confidence. There's also other ways to communicate. I've got a CLI text interface, a texting interface, and I'm building a web dashboard. So I've learned some lessons so far. Experiment and observe before you optimize. Everybody talks about that. You need to do it. You can tune the Imagenode computer vision parameters, and you can spend a lot of time tuning them because if you tune them well, the results are much better. So I spend a lot of time tuning. I also spend a lot of time optimizing network load. You want to send the smallest image size that'll get the job done, remembering that most object detectors need 300 pixels or less in terms of image size. And you can compress images to JPEGs. That saved me a lot. I tend to do that all the time around here, and it looks like a Gaussian blur anyway. Here's some quick passes on hardware examples. There's some infrared lights and other floodlights. There's a MOSFET that controls a floodlight. Get to know your MOSFETs. That's the best friend you have to keep your GPIO board on your Raspberry Pi from getting burned out with too much current. I also use light fixtures. There's a Raspberry Pi and a temperature sensor and a light fixture on the back of the house. Fake security cams. $5 little fake security cam holds a Raspberry Pi and a Pi camera. And I've learned a little bit about these tricks as well. PiCameras versus webcams, no contest. Use the Pi camera. Learn to use the Pi camera module. You won't regret the time spent. There's all kinds of waterproof enclosures, but my favorites are the mason jars and things like the old shingles on the barn. Infrared lighting, it's kind of tricky. I need to usually use 2 floodlights instead of 1, but it works out. And power, I use 12 volts rather than 5 volts if I'm running power any distance. And then I use a cheap car lighter kind of plug, like your cell phone, to get the power down to 5 volts. So what am I doing next? Well, I'm trying to write some deep learning software that looks at these image pairs and tells me that the garden needs watered. On the left, you see a very wilted comfrey plant and a not wilted comfrey plant. It's the same plant taken before and after watering. So if I could use deep learning to recognize that change, wow, what a gift that would be to help manage my garden. So all these projects are on open source and on GitHub. The addresses are all there for you. And if you have questions about this talk, I'm going to suggest something a little bit different. I'm going to suggest that you actually ask a question by posting an issue on the Yin Yang Ranch GitHub repository. All the details are there, and they're also in the deck. Some other links for electronics, ZMQ, OpenCV, Computer vision tutorials in permaculture are shown on this screen. And lastly, I want to thank you. Especially I want to thank our PyCon 2020 volunteers who have put in a lot of time to do this the hard way, which is organizing all of us at home. Thank them, and thank you for watching.